Welcome to Lab 4. Here we'll be observing the motion of an oscillating spring swinging in an arc, and from the observations we can make a model that predicts the motion and the energy changes. We care because these models can be used to help us predict the motion pattern of rope swinging, and in extreme sports it can help keep people safe. We'll first go over some initial conditions that we found from the observed motion that will help build the models. Then we'll discuss the fundamental principles that we need, and then we'll explain how the prediction model was made and the assumptions that we held, and then we'll compare the differences between our observed and predicted data, and finally we'll end with some discussion questions. Right before the mass was released from rest, we found this to be the initial position, and since the mass was released from rest, the initial velocity is 0. Moreover, to make the predictions, we need to know that the mass of the object is 0.402 kilograms. And here we're making the assumption that the mass of the spring is negligible. Then, since the video is on Earth, we're using the gravitational constant small g, which is equal to 9.8 meters per second squared. To find the spring constant, we can use this equation where t is the period of oscillation. If we rearrange the formula, we can get k equal to this. And to find t, we can look at the graph with the observed motion, and in 3 oscillations, the time is 4.843 seconds. So if we take the average of that, we get the mass oscillates every 1.614 seconds. If we plug in these values, then we get the constant to be 6.09 newtons per meter. Now that we have some initial conditions, we can use Newton's second law to find the resting length of the spring. Let's look at the forces interacting with the mass. We have spring force and the gravitational force. So F net is equal to the force of the spring plus the force of the earth. Since mass starts at rest, velocity is constant, so F net can be equal to 0. This means that the magnitude of the gravitational force is equal to the magnitude of the spring force. So we get mg is equal to ks, where s is L minus L naught. Then if we solve for L naught, we can get 0.0531 meters as the resting length of the spring. Now we can use the energy principle to predict the changes in energy of the mass. We'll consider the system to be the spring, earth, and the mass. This means that the total change in energy will be equal to the change in kinetic energy from the mass plus the change in gravitational energy plus the change in spring potential energy. Again, note that we are assuming that the mass of the spring is negligible, so that it does not contribute to the kinetic or gravitational potential energies. In the system that includes the spring, earth, and mass, there are no interactions or work happening between the system and surroundings if we neglect air resistance, so the change in energy can be set to 0. Knowing that, we can start building our model by specifying these values for the respective energies. Then we can code in GlowScript to calculate the energy changes. If you'd like to see this in more detail, check out the link in the description below. When we run the code, we see how the energies oscillate. Specifically, with the changes in gravitational potential energy and spring potential energy, they have the same sizes, but they're in opposite direction. So when U grav increases, U spring decreases, and vice versa. We can also see that the changes in kinetic energy oscillate twice as fast as the potential energies. And if you look at the yellow line here, the total change in energy stays at 0 throughout the motion. If we want to compare the blue predicted ball to the red ball, which shows the observed values, the red ball seems jumpy because the time between each observed position was 20 times longer than the predicted, so the motion of the blue ball is a lot smoother. Here the graphs compare the predicted and observed motion in the x and y direction of the mass. As you can see, they're not perfect, and to improve in the future, we can account for the mass of the spring and for the drag force that we emitted for the slab. And we can also account for the motion that happens in the z-axis. So, is the energy principle satisfied? Yes. As we discussed before, the system includes the earth, mass, and the spring, and the change in energy is equal to 0. Now let's look at how there's 2 different oscillation periods from the x motion and from the y motion. If we change the oscillation period, This would change what we got for t and therefore change what we got for our spring constant k, changing our predicted model.